Hi students, welcome back to geology. This last video in our mineral series is looking at the physical properties of minerals that we can test. So what happens when we test a mineral? Okay, so taking a look back at that same slide from the last video, what are the diagnostic properties of minerals? Luster, streak, hardness, color, crystal form, we've covered already. Now we're going to look at cleavage, fracture, hardness, specific gravity, and then we'll also discuss some of the other diagnostic properties while we're at it. All right, so first up is hardness. Hardness is the measure of the mineral's ability to scratch or not scratch other substances. So it's essentially the robustness of a mineral against other objects. And so we use something called the Mohs hardness scale, which gives us a scale from 1 to 10 to rank our minerals. And so we use a few different tests. We have a fingernail that we can use, which is 2.5, a natural fingernail, not like acrylic nail or gel nail or anything like that. So a natural fingernail is 2.5 on the hardness scale. A copper penny is 3.5. A wire nail is 4.5. A glass plate and a knife blade are 5.5, and the streak plate is 6.5. You'll see in lab that we're going to use a fingernail, copper penny, and we're going to use a glass plate. Okay, and we're going to take each of those minerals and see if they'll scratch that object. If it scratches that object, it's harder than that object. And then we would place it somewhere on this hardness scale. Here's another graphic for you that shows you some of the same minerals, a few of them different. This is from the National Park Service. It's a really helpful visual for students to see that talc is at the bottom of the hardness scale and diamond's at the top. Diamond is the strongest substance, and talc is one of the weakest substances. So one of the things that hardness also helps us with, other than identification, is that it helps us know what we can use minerals for. So for example, if we wanted to make a glass window pane, would we want to use something like gypsum that's low on the hardness scale? Well, probably not, because it's going to be really easy to break. Conversely, when we're making things like baby powder, would we want to use something like topaz to make that baby powder? Probably not, because then it's going to be pretty rough. You're going to want to use something like talc, something that's nice and soft. Okay, so moving on from hardness, we're going to look at cleavage. Cleavage is the way that a mineral will break along planes of weakness. So this is when the mineral starts to break. What is it going to do? Is it going to break along specifically weak bonds between its crystal lattice? Or if it doesn't necessarily have specific weak bonds, maybe it will fracture, which we'll get to in a second, and it'll just break randomly. So this is an example of muscovite. As you can see, there are weak bonds going in the vertical direction, and going in the horizontal direction, there are strong bonds. So this mineral will break along those weak bonds, creating that single, there's only one cleavage plane of weakness. Okay. Now, different minerals are going to have different number of cleavage planes. So we looked at muscovite, which is A there, and that only has one cleavage plane in one direction. Okay. If we look at another example, like a feldspar, which I have an example of right here, these have two, and then it also notes an angle. So one thing you want to do is when you're figuring out if it has cleavage or not cleavage is you want to find sets of parallel sides. So you can see that there's a set of parallel sides there, and then there's another one there. But these two aren't parallel. Same thing with the graphic there. And so this one has 1 and 2. So finding pairs with your fingers is probably the easiest way to go. And then you want to look at, does it meet at 90 degrees or not 90 degrees? Okay, if it meets at 90 degrees, we call it two directions at 90 degrees. If it weren't to meet at 90 degrees, like the hornblende in C, you would say it's two directions not at 90. Okay, and it can go all the way up to 4. So fluorite has 4 cleavage planes. And in that, you wouldn't necessarily say what the angle of intersection is, because just like muscovite, we're looking at something that's completely off. It's not going to be 90 for sure. It's going to be not 90. And with muscovite, there's nothing else for it to interact with, so we just don't even talk about it. Or we just say not 90, because there's nothing for it to interact with. And then you have calcite and halite there, which both have 3 planes of cleavage. but one is at 90 and one is not at 90. And so hopefully you can kind of see those angles and those differences there. So that's cleavage. We're looking for sets of parallel sides, and you can use your fingers to do that. With fracture, this is a random breaking pattern. There's not a flat parallel side you're looking for, it's just irregular breaking. Most of fracture is irregular, some of it is conchoidal. And conchoidal fracturing is where you have, usually in like a glassy, very glassy mineral like quartz, you have these half semicircles that kind of form. And so if you can kind of see those lines in that quartz crystal moving through kind of concentric on that specimen, those are your conchoidal fractures. Whereas on the left, you're looking at a specimen that has no particular pattern to its breaking. Okay, so it's just random, it's just irregular. All right, moving on to some other things that are in, well, specific gravity is in most of them, but some of the other ones we'll look at in a second are only going to be in certain minerals. So specific gravity is going to be basically the density of the mineral. So you need the mass and you need the volume. So density is mass over volume. At the top there on that photograph, you see them weighing the specimens. That gives you the mass. And then underneath, we're looking at the volume. So we look at the difference in water level, and that gives you an approximate volume for that specimen. So you would get the mass over volume. That would give you the density of the specimen. Some of them will be magnetic. I think I mentioned that in one of the other lectures. And if they have iron oxide minerals, they're going to be magnetic. And things like magnetite, which you see there in the photo, will attract metals and other magnets. I have this image of kind of this like black dust that looks like it's moving around. In a lot of museums, they set up magnetite in powder form, and it's like in this big bowl, and you can kind of move around magnets, and it moves around the sand. It's really just magnetite that you're moving around. All right, some will glow under UV light, which is called fluorescence. So in lab, we have some specimens that have rubies in them and sodalite, and both of those will illuminate like these images here under UV exposure. Some minerals will smell funny, like sulfur in the middle there, that yellow mineral. They might taste a specific way, like halite tastes like salt because it's salt. And they might feel a particular way. So that's kaolinite on the right there. Kaolinite is very powdery, so you might have powder come off on your hands. Another good indicator for one of our special minerals, which is feldspar, we have plagioclase feldspar that we look at and potassium feldspar. The difference between the two is whether they contain striations. So this is a definitive marker for knowing whether you're looking at plagioclase or potassium feldspar. So our potassium feldspar does not contain striations, but our plagioclase feldspar does. Striations are a growth pattern or mineral habit that creates kind of these scratches within the internal structure of the mineral. And so you can see all those lines that are in each of the photographs with the exception of the one at the top right. All of those parallel lines to each other, they look like hairline grooves, and those are our striations. The easiest way to see them is to turn the mineral and try to see it reflected in the light. Okay. If it contains the striations, this is plagioclase feldspar. If it does not, this is potassium feldspar. So the top right photo there is an example of what potassium feldspar looks like. One of the minerals that we work with, known as calcite, will have double refraction. So this is when light enters the mineral and travels through it. It creates two different rays, and so it gives you kind of a double feature. It gives you two different images of whatever the mineral is over. So you can kind of look through the mineral and see the two different rays of light passing through it. And then minerals that contain calcium carbonate or a base will react to acid. So we won't do this, I won't do this with minerals, but we will do it with rocks. And I'll show you how very dilute hydrochloric acid can react to calcium carbonate in these rocks, which formed from minerals that had calcium carbonate in them. And then last but not least, we have the Bowen's reaction series, which will give us a segue into volcanic rocks, igneous rocks. When a magma is crystallizing, the first thing to crystallize is going to be things like olivine there at the top at the highest temperature. And then quartz crystallizes last. I mentioned this in one of the previous videos when we talked about the mineral groups. And so quartz is last to crystallize, and it creates a different igneous rock type. Olivine, we're looking at ultramafic, and with quartz, we're looking at granitic. And we'll get more into this. We'll see this again when we look at igneous rocks. All right, some final thoughts. Minerals are the building blocks of rocks. Rock-forming minerals are most geologically important. So we're not going to look at all minerals. There's 4,000 of them. We're focused on basically 20, which are our most common rock-forming minerals. The physical properties are how you're going to distinguish between the different minerals. And lastly, in your notes, I want you to jot down why cleavage occurs in some minerals, but not all minerals. All right, that wraps up minerals. I'll see you guys in the next series. Bye.